Hello, welcome to PhyzQuest. So in the previous video we have discussed about the integral theorems of vector calculus and we have discussed about the Gauss divergence theorem. In this video we will cover Green's theorem and the Stokes theorem. So let's talk about the Green's theorem. So here by definition Green's theorem transforms the line integral of a vector field around a contour into the integral of the vector field over the surface bounded by the contour. So here let us suppose we have a vector field F, and let us consider this vector field F lie in a two-dimensional plane, that is suppose xy plane, let us consider. So vector field we have considered is a two-dimensional vector field F which is lying on this xy plane. Here it is a surface S enclosed by contour or closed curve C. So your F is a two-dimensional vector field in xy plane and S is the surface of the plane enclosed by the contour C. Now let's try to understand this theorem. So it mentions that it transforms the line integral of a vector field to the surface integral of a vector field. So how it transforms? See, line integral of the vector field is represented as integration over closed curve C f dot dl. This symbol is a symbol of close, that is C means it's a curve. So it's a closed integral is taken over a closed curve C. F is your vector field and dl is because it's a line integral considered. So now we have to understand this term first of all. So the line integral of the vector field over a closed curve C, what it represents? First of all, let's consider a simple integral, means let us suppose it's a simple curve, it's not closed. Suppose this symbol is not there, suppose. So in that scenario, this line integral or the vector of the vector field over the curve C indicates how much the vector field is aligning with the curve C. So if we consider here, suppose this is not closed, this is open at this point, suppose. So the line integral of vector field taken over this curve will be how much the vector field is aligning along this curve. This is what the line integral represents. Now when this curve is closed, that means in this case, so if the curve is closed, that means now it indicates that how much the vector field is trying to circulate around the curve. Why circulate? Because it's a closed curve. That means when the vector field will try to align along the curve, it will continuously form a closed curve or try to circulate here along the line of the curve. Therefore, this integral over the closed curve C or the line integral of the vector field over the closed curve C indicates the circulation of the field around the contour C. Now we have already discussed in the differential part of the vector calculus that any kind of circulation is related to the curl operation. Therefore, circulation of the vector field implies curl of the vector field. Now curl of the vector field is applied to a three-dimensional scenario because it has three components. So now here the situation we are considering here is a two-dimensional case because we are considering xy plane. Now what to do here is xy plane, if the field is lying in xy plane, so if you want to take the curl of this, we can only have the z component of the curl. That is because of if we apply the right hand thumb rule, in that scenario xy plane, if you consider the curl will have to be to a non-zero part. To have a non-zero value of the curl, we must have the z component for xy plane. So z component of the curl of the vector field will be, in this scenario, will be del f x by del y minus del f y by del x. So here if we put this and write it down, so this will be integration over s del f y by del x minus del f x by del y ds. So this finally represents the mathematical part of the Green's theorem. So this is for xy plane. If we change the other plane, this also will change. So now here we have discussed about the the definition and the practical understanding of the Green's theorem. Now let's talk about the application of the Green's theorem. Now most practical application of Green's theorem is our daily used to scenario is the example of a cyclone. Cyclone, as you can see, it's a planar thing. Its formation is a circulatory motion it shows. Therefore, it's the best example of a circulatory motion and therefore Green's theorem. Now another is from mathematical point of view. It is the application can be calculation of the area of a planar surface by integrating its perimeter. Suppose you are given the equation, suppose you are given any planar surface whose perimeter equation is given. So you can calculate the area of that surface by integrating its perimeter equation. So these are a few application of Green's theorem. Now let's talk about Stokes theorem. So Stokes theorem shows that it relates the integral of the curl of a vector field over a surface to the line integral of the vector field over the contour bounding the surface. So again, if you try to write it down mathematically, this, suppose we have a vector field f. So if you write down mathematically, it will be integration over the closed curve C f dot dl, this is the line integral of f, is equal to integration over the surface S curl of f ds. So this is the surface integral of S. So here again, here it is transforming the line integral to a surface integral, which is very much similar to the Green's theorem. So therefore, only difference is Green's theorem we have considered a two-dimensional case. We have considered xy plane, whereas it is a three-dimensional case. So we can say that Stokes theorem is a three-dimensional extension of the Green's theorem. In Green's theorem, we use a planar surface like we have used xy plane in the previous case. But in case of Stokes theorem, we use a three-dimensional surface or any kind of a oriented surface. So here, this is the first thing. Second thing is, here we are talking about the vector field is in considering the surface, the vector field is lying on a surface which is enclosed by the contour. Now here this surface we are considering the bounded by the closed curve need not be specific. This means, suppose we have considered this case here. We have a closed curve C. Now this includes or this encloses two surfaces here. First is S1. It is a oriented surface. This surface is flat, but it's a oriented surface. Both are, in the second surface is a curved surface. Both are enclosed by this curve C. So they have the same boundary, and this means there is not a fixed thing that any particular surface you have to consider. That means curve C can include any kind of surface. So now here in this scenario, if we try to calculate the surface integral of over these two surfaces, or either this flat oriented surface or this curved surface, the surface integral of both S1 and S2 will be same because they have the same boundary C. Now coming to the theorem here. The mathematical point says that integration over the closed contour C of the vector field, the line integral of the vector field over the closed contour will be same as the curl of the vector field over the surface enclosed by the contour. So how it is similar? See, line integral of the field, as we have previously discussed in case of Green's theorem, this indicates the circulation of the field along the contour, and circulation is perfectly represented in case of curl of the field. And here, since here, though in case of Green's theorem we have a two-dimensional case, therefore we have to write as the component of the curl, but here it's a three-dimensional case in case of Stokes theorem. So you can perfectly write down the circulation of the field as the curl of the field directly, that is del cross F over the surface S. So this proves the mathematical form of the Stokes theorem. Now let's talk about the application of Stokes theorem. There are many applications. Most important application is in electromagnetic theory. So electromagnetic theory, here one of the most important theorem is the Faraday's law. So Stokes theorem is used during the conversion between the integral form and the differential form of the Faraday's law of the electromagnetism. So we can convert the integral to differential form or differential to integral form. So first of all, Faraday's law, the mathematical form of the Faraday's law is integration of closed curve E dot dr is equal to minus del by del t of integration over the surface S B dot ds. This is the differential form of the integral form of the Faraday's law. So now if you apply Stokes theorem here, this line integral can be easily converted to a surface integral, that is it will be del cross S, and here we have already a surface integral, so we can say this is del b by del t taken over the surface S. So if we compare both the sides, or we can take this term to this side and ultimately take out the integral term, this will lead, we can get a differential form of the Faraday's law, which is del cross E plus del B by del T is equal to 0. So this is one of the Maxwell's equation. Now here, this is the Faraday's law we are talking about. Now second application will be in case of magnetostatic. Now in magnetostatic we have a Ampere-Circuital law. Here Ampere-Circuital law is represented as mathematically, this is integration over B dot dr is equal to mu 0 I. So B dot dr, this is actually your magnetic field, and mu 0 I is your current. So this is the line integral it's taken, which is equal to mu 0 I. So this can be written as I is the current, so it can be written in terms of integral of current density, or surface integral of current density, we can write it down, which is equal to mu 0 integration over S j dot ds. Now this line integral of the magnetic field we can write as surface integral of the curl of the magnetic field. So this will be del cross B ds. So if we compare this and this term, we can write down the differential form of this law as well, which will lead to the differential term of this law, which is del cross B is equal to mu 0 j, which is another Maxwell's equation. So these are two of the applications of the Stokes theorem. So in the first part of the video we have discussed about the Gauss law, its a practical example and its application, and here we have discussed about the Green's theorem and the Stokes theorem and its practical example with its application. So this covers all the integral theorems related to the vector calculus. So far we have done the problems of the CSI net and gist. From now onwards we will gate problems.